And ladies and gentlemen, welcome to our next video, Calculus Notes, Section 8.3. I thought you might like this. You young ladies may not enjoy the punchline at the end, but just a good comparison of how our orbit compares with other planets, and then, if you will, how women are the downfall of so many brilliant men over the years. But if you want to keep reading, that's fine. Otherwise, we're going on. Today, ladies and gentlemen, we're going to talk about relative rates of growth. We are using limits and L'Hopital's rule, if you will, to compare how different functions grow. Remember, growth is how steeply it climbs, how steeply a function climbs. So we're going to be deciding which ones climb steeper than others and so on today. This is very important for us, as this does help us describe end behavior, which is extremely important in some things later on. Now, ladies and gentlemen, this is the main part of the lesson, this slide here. If you have two functions f and g, and we want to know, as x becomes really large, what are they doing, which one is growing faster, what we do is we compare f and g in fractional form, and we take the limit as x approaches infinity. Now, if when you take this limit as x approaches infinity, if you get infinity as an answer, then that suggests that whatever function is on top is growing the fastest. If, however, when you compare f and g, if you get 0, that would suggest that the function on the bottom is growing the fastest. Because think about what's happening. If the one on top is growing faster, then the numbers on top are becoming much larger, much faster than are the numbers on the bottom. The ones on the bottom can't keep up, so the function's just going to keep getting larger and larger and larger. On the flip side, if the bottom is growing faster, then the growth of the top can't keep up with the bottom, and the number is becoming smaller and smaller and smaller and smaller until eventually it does go to 0. Now, what if you don't get infinity and you don't get 0? Then that means that they grow at the same rate. They're both increasing at the same relative rate. Alright, our job is to show that e to the x grows faster than x squared as x approaches infinity. So we begin with the limit. We take the limit as x approaches infinity of e to the x over x squared. Now, if e is growing faster, then this limit should turn out to equal infinity instead of 0 or some other number. So we look at this. I see that it is an indeterminate form, infinity over infinity, so we apply L'Hopital's rule. Currently, it is still an indeterminate form, infinity over infinity, so we do L'Hopital's rule again and get down to this. Now, if I were to plug in infinity, I have infinity over 2, which is just infinity. There at the bottom of the screen, if I can move down just a little bit. Since it is infinity, that would suggest that e to the x grows faster than does x squared. Alright? What about natural log x? Does it grow faster, slower than x or x squared? Alright, well, I'm going to suggest that it grows slower, and we're going to prove it. So we'll first of all compare it to just x. We'll take our limit here. Now, if natural log is going to grow slower, then as we take this limit, this should end up equaling 0. So if I were to plug in infinity, I have infinity here, I have infinity there. Again, L'Hopital's rule. Derivative is 1 over x, derivative of x is 1. Now if I plug in infinity, 1 over infinity is 0. So if it's 0, that would suggest that the top is growing faster. The top is growing slower than the bottom. Now we'll compare to x squared, and again I have infinity over infinity. So we'll apply L'Hopital's rule. 1 over x and then 2x on the bottom. You can simplify that to be 1 over 2x squared. Now if you plug in your infinity, you do have 1 over infinity on bottom, and that is 0. So you see natural log x is slower than both x and x squared. Now that makes sense if we think about it, because we know that x grows like that. We know that x squared grows like that, and you see both of them have some steepness. And natural log x actually starts leveling off as you go. So you see its growth is much, much slower. And we'll get rid of all that. Alright, another example. Let's compare x with x plus sine x. Alright, and this one says show that they grow at the same rate. Now, And it's going to give you a caution here. A lot of people think that in order for things to grow at the same rate, if you're dividing them, you have to get 1 as an answer. That's not the case. If you get 1 as an answer, that means that they're the exact same thing, but not necessarily growing at the same rate. So our goal here, when we do this limit and make our comparison, is to not get 0 or infinity. Now, if I were to plug in infinity right now, I do have infinity over infinity, so we must apply L'Hopital's rule, or we could simplify. X over x is 1, sine x over x. Now, if I were to plug in my infinity, this is on top, negative 1 to 1. That's the range of sine, negative 1 to 1. And that over infinity would be 0, and then 1 right there. So in some simplification, we avoided L'Hopital's rule, and then the answer is 1. It doesn't have to be 1. It just has to be a non-zero, non-infinity number to suggest that they grow at the same rate. Now, what I would suggest that you do is you make a sketch of this, and then you start looking as x approaches infinity. You start scrolling out as far as you want to take it until you get bored with it. And what you'll see is that the sine and the x plus sine actually start looking like the same rate of growth for each of the graphs as you get to infinity. Alright, comparing logarithmic functions. So what about log base a of x and log base b of x? Just logs of two different bases. Do they grow at the same rate? Well, it says they do, so let's see. I'll start with the limit as x approaches infinity of log base a of x, log base b of x. Now I'm kind of stuck here. Now there are a variety of things I can do, but both of these do give me infinity over infinity, so I either need to do L'Hopital's rule or I need to simplify. And I'm going to simplify using a change of base formula. Now I know we think change of base is obsolete because of what our calculators can do, but the fact is that it is still useful in some situations. Now, given this, I can do some simplification. You'll notice the natural log x, they will cancel. And I have this, the 1 over natural log b can flip to the top. And now when I look at this, notice that there's no longer an x in which to plug in my infinity, so that means that it is a constant term of growth. 1 is not growing any faster than the other, so comparatively speaking, it's a constant term or a constant rate of growth. Transitive property of growing rates. Now you know what the transitive property is. If A implies B and B implies C, then A implies C. You've learned that since Algebra 1. Rates of growth are the same. If F grows at the same rate as G, and G as the same rate as H, then we could say that F and H grow at the same rate also. So our job is to show that the functions below grow at the same rate as x approaches infinity. Now, rather than compare this one directly to this one, I'm going to compare this one to x, and then I'll compare this one to x, and if they both grow at the same rate of x, then I know that they both grow at the same rate together. So I look at this. I'm plugging in it's infinity over infinity. You can apply L'Hopital's rule, or we can simplify. I'm going to simplify by putting everything inside the radical. So you put x inside a radical, it becomes x squared. You can simplify now. I'm going to have to move my screen down just a little bit, so let me do that. See if I can do that without. There we go. Almost. There we go. You can simplify x squared over x squared is 1 and 5 over x squared. Now I can plug my infinity in, and I get 0 for this part right here, and that does give me an answer of 1. So that has shown that this function here, radical x squared plus 5 and x grow at the same, which makes sense because the square root of x squared is x, so that would make sense that they grow at the same rate. Now let's make sure that the second function also grows at the same rate of x. So we have this, we have infinity over infinity again. So I'm going to move this inside the square. Now just like over here, to put something inside a radical, you square it, you do the opposite. So if I'm going to put this one inside of a square, I do the opposite, I take the square root of it. And now, just like I did on the previous problem, I can split it up into each individual part and simplify, and that gives me this. Now if I plug in my infinity, this part goes to 0, and I do have 2 squared, which is 4. Now these don't have to be the same number, but because this is not 0 infinity or infinity, and this one is not 0 infinity, then both of these grow at the same rate as x, and therefore both of them grow at the same rate as each other. Now we end today not completely different topic, but a slightly different topic: sequential versus a binary search. Just a little bit of information for you, since we're talking about a chapter on sequences. A sequential search, ladies and gentlemen, and we'll define these in terms of this problem. You pick up a dictionary, you're looking for one word, and it says that there are 26,000 words that begin with the letter A. Now, to look for the one word, one way you could do it is to start at the first word, and then if that's not it, go to the next word, and if that's not it, go to the next one and the next one, and you just keep going until you find your word. In other words, there is a specific pattern or sequence that you are following in order to find your word. This is called a sequential search. But if you are going to enter into a math and science field, specifically computer programming, you're going to learn that sequential searches, while we like sequences in this chapter, are probably not the best way to do a search, especially for very large sets of data. Rather, a binary search is needed. Now, what's a binary search? Well, we go straight to the middle of the list, and if you don't find the word in the first half, you go to the next half. And if the word is not in that half, after you've cut it, if the word's not in the first half, you take the next half, cut it in half, and so now you're searching a quarter, and if it's not in the first quarter, look at the next one. And if it's not in that group, then you take and you just keep cutting groups in half. So let me get a clearer screen here just to give you an example. For instance, if we have, we'll say they'll say that represents all of our words. So first of all, we cut it in half and we look in just the first half. If it's not there, we go to this next part, we cut it in half, and we look. If that's not there, we cut that in half, and we look. And if that's not there, we go to this part, cut it in half, and eventually you're going to do that until you end up finding your word. This is called a binary search, and most computer programmers, if you are dealing with very large sets of data, prefer this over just a sequence search, which is start at the first, go to the next, and just keep going and going and going. So in general, for a list of length n, how many steps are required for a binary search? Well, let's start with an actual number. Let's start with 8. Let's say I have 8 objects, and I want to see if it's in those 8 objects. How many steps is it going to take at most? Now remember, this is at most. Well, I take the first half, and let's say it's not in that. So then I'm left with 4 objects. I take those 4, I look in the first half of those 4, let's say it's not in that. So I'm down to now 2. And I look in those 2, in other words, I look at the first one, and let's say it's not the first one, then it must be the last one. Now how many searches did that take? 1, 2, 3. So 8 took 3 searches. Okay, so let's try, I don't know, 32. 32 could go down to 16. 16 could go down to 8. And then we saw up here to 4, 3, 2, and then eventually 1 if you have to. How many searches is that? 1, 2, 3, 4, and 5. So 32 yields 5. Now what's the relationship between these numbers? Well, I know that 8 is 2 to the 3rd. I know that 32 is 2 to the 5th. So what's the relationship between these two? And let me make all this ink disappear. The relationship is this right here. If you do log base 2 of however many terms it is that you have, and I got to go back because I hit the wrong button. If you do log base 2 of the number of items that you have, that gives you the maximum number of steps required in order to obtain your item. Much faster than now. You could say, well, what about the sequential? Or what if what you're looking at is at the very beginning? Well, that's true. What if it's at the very end? So this actually is much preferred by computer scientists. And that, ladies and gentlemen, is the end. You only have one video to watch today. And bring all your questions in class tomorrow.